Well, hello there. This is Miss List, and I'm here with AP Chemistry, section 4.2, which is on net ionic equations. First, I'd like to do a little review of some of the things we talked about in our equations introduction. So, chemical and physical processes can be represented symbolically by equations. And here we have an example of our chemical equations. This is an example of photosynthesis, actually, where we've got carbon dioxide reacting with water to make sugar, that's the C6H12O6, and to form 6 oxygen molecules. So the number out front is called a coefficient. It's telling us how many CO2s there are, and that's true for across the entire chemical reaction. Anytime we have no coefficient, we assume that's a 1. And so we can actually think of this as like 6 carbon dioxide molecules plus 6 H2O molecules will make 1 sugar molecule and 6 oxygen molecules. The subscripts are telling me how many atoms of each element there are in a particular compound or molecule. Again, if there's no subscript, we assume it's a 1. We also have states of matter listed. So gas is G, L is liquid, S is solid, and we have one that's not on here, but we're going to become very familiar with it today, and that is aqueous. That means it is a solution, and the solution is a water-based solution, hence aqueous, aqua, water. We also need to keep in mind that we have diatomic elements like oxygen. We talked about that in the last video. It's only diatomic when it is riding solo. It has some other friends that also do that as well. That is not true though when it is in a compound. So here over with water, notice we do not have a 2 next to oxygen because that's not how it combines with water. Once you've mastered chemical reactions though, we always take it a step up and start talking about what's called a net ionic equation. And net ionic equations are specifically, we see them most often in a double replacement reaction. We can occasionally see them in other types of reactions, but double replacement is definitely going to be the most common place that you see them. In order to write successful net ionic equations, because most of the time we're looking for a precipitate, and a precipitate forms only when something is insoluble. And so when we're looking for a net ionic equation, it's important to be able to identify what's going to be soluble and what's going to be insoluble. The easiest ones to remember are the SNAP ions, and I call them SNAP because it is sodium, ammonium, nitrate, and potassium. Anything containing those are going to always be soluble. Anything outside of that, then we would have to use our best judgment to try and figure out what is the precipitate or not, or we can consult a solubility chart or solubility rules. I don't think it's super important to memorize all the solubility rules, especially if you know the SNAP ions. That takes care of a lot of the examples you're going to see. However, if your teacher insists that you memorize them, then follow what your teacher says. So the idea behind a net ionic equation is it only shows the particles that change in the reaction. It cancels out what we call the spectator ions. And just like spectators watch at sporting events or concerts, a spectator ion is not participating in the chemistry. They're there, but they're not involved. So here's a very good example that kind of walks through each step. We always want to start with what's called a balanced equation, and that's what we were practicing a little bit towards the end of 4.1. This is a double replacement where lead nitrate and sodium chloride are rearranging. Remember, with double replacement, we have outsides going with insides, so lead is going to form with chlorine, and sodium is going to form with nitrate. Sodium, when it forms with nitrate, is always soluble. So that's why I've marked it with the aqueous. The lead chloride is actually insoluble, and that is going to be my precipitate. That's important because when you break it down into what we call the complete ionic equation, we're going to break apart everything that is aqueous into ions. So lead ends up by itself. We do have two nitrates, so we show that with a coefficient of a 2 for nitrate. We have two sodiums and two chlorines. Again, I'm breaking up everything that is aqueous, including on my product sides. I have two sodiums and two nitrates. And the only thing I'm not breaking up is my solid. Remember, I can only break up the aqueous ions. From here, what I'm gonna do is I'm gonna cancel out the things that appear exactly the same on both sides. And I've highlighted them in red. Nitrate doesn't change at all. So that's one of our spectator ions. So I actually get rid of that, cross it out. And then sodium, I've got 2 Na plus on the left and 2 Na plus on the right. So that is my second spectator ion. And so what we're left over with is lead combines with 2 chlorine ions to form lead chloride, my precipitate. And this is what we call a net ionic equation. So some take-home points. We have to start with a balanced chemical equation. We have to do that first. Step 2 is to break apart our balanced equation by separating anything that is aqueous. Then I'm going to cancel the things that appear on both sides, and they have to appear exactly the same on both sides. And then I'm going to rewrite what's left over, and that is what we call the net ionic equation. And this is what is really happening in the chemical reaction. If this was happening in the beaker, I would see lead chloride down here at the bottom, and our spectator ions are still here. Sodium and nitrate are still present. It's just they are in solution. They're in aqueous. So the actual reaction I see, because I'm not going to be able to see the ions, but I will see the precipitate, and that is why we focus on the precipitate when we do our net ionic equations. So one application of this is to be able to determine if something's an electrolyte or a non-electrolyte. And this is just practice breaking things into their ions. And this happens specifically for ionic compounds. And so like lithium chloride, that's an ionic compound. So this would be, yes, an electrolyte. And what that means is that when I have lithium chloride solid and I dissolve it into water, the lithium ion and the chlorine ion are going to separate. And that's actually what allows ionic compounds to conduct electricity. We talked about that a little bit in Unit 2. They only conduct, though, when they're dissolved in water. If I have something that is covalent, that is going to be no. It is not going to conduct electricity. And so if I wanted to show something that's covalent, changing from a solid into a liquid or dissolving, it is not going to break apart at all. The only thing we would do to show that is that we would change that to be aqueous to show that it's been dissolved in water. This letter C is a compound that is ionic, so we can show it breaking apart. We've got NH4, 2, and then SO4. And on the left of the arrow, it is a solid. On the right, we want to show it breaking apart into ammonium and sulfate. That is the SO4 component. Again, marking it with aqueous to show that it's dissolved in water. We do still need to maintain our balance, so that's 2 NH4s because I have the 2 subscript. Strontium hydroxide is, so I can show it breaking apart into strontium ion and hydroxide ion. Again, need to make sure it's balanced, so we do include our coefficient of 2. And then finally, our last one is covalent. Again, all nonmetals is what makes this covalent. So when I show it changing or dissolving in water, and this is sugar, I am simply going to rewrite the same structure. We're not breaking anything apart because it stays together as one unit, and I'm just simply changing the label to aqueous. So on Our next example, it says, draw a particle level diagram to show lithium chloride in solution, and then describe why this solution would conduct electricity. So what they want us to draw is lithium, and they want us to draw the water molecules around it. So lithium being a positive charge, I'm going to have the negative side of my very polar water molecule, which is the oxygen side, face towards the lithium. And it didn't say how many to draw, so I'm just drawing a few. So the oxygens should all be facing towards lithium. For chlorine, it would be the opposite. I would have the hydrogen, which is the positive side of the water molecule, facing towards chlorine. And again, this is the reason we do this is because that's going to be an ion dipole interaction between the water and these ions. So we can show that with dashed lines if we want, but that's kind of the idea we were going for here. And describe why the solution would conduct electricity. When ions are dissolved, it allows electrons to flow. And that's what electricity is, it's a flow of electrons. So here is an example where we are actually going to go through the process of writing a net ionic equation. It says aqueous solution of silver nitrate, which is AgNO3, aqueous, and it's AgNO3 because silver is +1 and nitrate's -1, is added to an aqueous solution of sodium chloride. Sodium's +1, chlorine is -1. It says a white precipitate AgCl is formed. They don't tell us what the other product is, but we can use reasoning skills to figure out that that is going to be NO3. And that's going to be soluble because the snap ions, this contains both snap ions, Na and nitrate, which means those are always soluble. So here is an example of the balanced equation. I don't need to add any coefficients because they were all +1, -1. The next step is to write what's called a complete ionic equation. And this is where I break up anything that is aqueous into its ions. We leave our precipitate alone. It does not get broken apart. And then finally, we want to cancel out our spectator ions. And our spectator ions are going to be the ones that appear exactly the same on both sides. So that's going to be nitrate and that's going to be sodium. Another way to think about it is we want to show what is making the precipitate. So Ag aqueous forms with chlorine aqueous, and AgCl solid is what forms. So this would be my complete ionic, or my net ionic equation after my spectator ions are canceled. Now, once you've gotten the hang of this, if I know that it's the ions that make the precipitate that make my net ionic equation, it is possible to go straight from the balanced chemical equation to your net ionic equation. A lot of times on tests and the AP test, they don't ask for that intermediate step. They ask just for the net ionic equation. So if you're comfortable with that, you can skip right to from A to C without making that B part. However, a lot of students, they need to see it all written out so that they can visualize what's being canceled. So if that seems like too much of a challenge for you, then follow the steps that we talked about. Let's look at a couple more examples. Our next one has potassium phosphate. That's going to be K3PO4 because of how the charges are balanced. And it says both of these are solutions. It's going to form with aluminum nitrate. This is going to be a double replacement reaction. So aluminum is going to go with phosphate and K is going to go with NO3. Now, this one does not tell me what the precipitate is. I have to figure that information out. And the way I do that is knowing my snap ions, because K and NO3 are both snap ions, which means that this has to be my precipitate and that these would be aqueous. Now, I do need to balance it because I do have 3 potassiums and 3 nitrates on the left, so I need to put 3 of each of those on the right. Next, we're going to break apart into our ions. So I need 3 potassiums. Again, it says to include states for each of these. So I am including the states. This is the step that isn't always necessary, especially if you can visualize getting from A down to C without doing this. It actually makes the problem a little bit shorter, and I can show that on the next example. And then finally, we are going to cancel our spectator ions, the things that appear exactly the same on both sides, and that's going to be my potassium, and that's going to be my nitrate. So I want to rewrite just the formation of my precipitate. I have phosphate ion combining with aluminum ion. Both of those are in solution, and it's going to form aluminum phosphate, and that's solid. One thing that is super important when you do net ionic equations, it is called net ionic. You have to include the charges. That is a must. So on number 5, I'm going to do the example where I skip from A down to C without doing the intermediate step, even though they asked for it. So first, we're going to start with our balanced reaction. It says copper chloride and sodium. Oops. We're assuming that these are solutions. It doesn't specifically say, but usually that's how these types of reactions work. Is I have 2 solutions and I mix them together. So copper chloride solution is going to react with sodium sulfide solution. And again, this is double replacement. So Na is going to go with Cl. Sodium is a snap ion, so I know that that is going to be aqueous. And then my copper is going to go with sulfur, and that is my likely precipitate. I do need to balance because I have 2 sodiums and 2 chlorines on the left-hand side. So I'm going to put a coefficient of 2 there. Now, I mentioned that you can go from A to C without doing B if you focus in on what is happening to make the precipitate. So if I know my precipitate is copper sulfide, then I can work backwards from there and say, oh, well, it's the copper. What's the charge on the copper? It's a 2. It was aqueous in solution. And I'm going to add sulfur to it, and it has a charge of 2, and together those would combine to form CuS. So it is possible, if you understand how these work, to jump and skip that intermediate step. It does save a bit of time. So now it says draw a particle level diagram showing the reactants from 5 and the resulting mixture. It says we do not need to draw water. So here I would draw 1 copper ion and 2 chlorines. That kind of looks bad. Let's try again. 2 chlorine ions. And then I'm going to draw my other one, which is sodium, and it's 2 sodiums for every 1 sulfur. And then my final mixture, my precipitate, is going to be CuS, and I'm drawing that as in the bottom. And that was just 1 Cu and 1 S. That's what came together to form my precipitate. And so what's left over is 2 sodiums and 2 chlorines. And those are going to be just floating in solution. Again, those are my spectator ions. All right, that is net ionic equation. It is a little tedious, but once you get the hang of it, I'm sure it won't be too tricky for you. As long as you feel comfortable with the snap ions, that is really key to making sure that you figure out what is the precipitate. All right, thanks everybody.